linear algebra done right by Sheldon Axler. So last time we left off, well, maybe 20 minutes ago, we left off in question 3, or rather exercise, all the exercises in section 3D, and now we're starting from section 3 finally. So we have t is a function from v to w. The graph of t is a subset of v cross w defined by graph of t is equal to vtv, where vtv is a subset of v cross w, or something stupid like that. Well, it's not stupid, it's kind of ingenious actually, how they imagine this kind of mapping as a subset of a graph. I never saw about like that. Prove that T is a linear map if and only if the graph of T is a subspace of V cross W. Yeah, I don't know about that. That seems kind of difficult. So first, I want to know what it means for a graph of T to be a subspace of V cross W, because it's not well defined here. So let's see what they have to say. It says formally a function T from V to W is a subset T of V cross W such that for each V in V there exists exactly one element V, W, and T. Okay. Yeah, that makes sense. And then in other words, formally a function is what is called above its graph. We don't usually think of functions in this formal manner. However, if we do become formal, then the exercise can become rephrased as follows. Prove a function T from V to W is a linear map if and only if T is a subspace. Okay, I mean, I don't see the difference. Maybe I'm not seeing this clearly. I feel like the explanation said very similar things. There may be some subtleties I just completely missed. So let's say we have this graph, right? So for this graph setup, I think the terminology is deceptive because you really just want to think of it as a set of coordinates or a set of associations, not really as a graph. Only in this way can you perform operations on those tuples, and in that way you can think of it as a subspace, because then you have your addition and scalar multiplication as usual. But if you think about it in terms of a graph, might be kind of confusing, so should probably not go there. Let's just think of it in terms of being a set of points. So let's say that T is a linear map. We assume this. And then, I think this way should probably be easy, actually. So let's choose arbitrary v1, v2 from wait, hold on, let me think. So given that this is a linear map, we want to show that for arbitrary, let's say C1, C2 in the graph of T, and also for arbitrary F in the field of scalars, we have C1 plus C2 is still in the graph of F, and also F times C1 is equal to, oh shoot, what is it's also in the graph. Also, we got the zero vector in the graph. And look, this shouldn't be difficult to show for the zero, because T of 0 is 0 because T is a linear map. We got this demonstration once again. Then T of 0 is 0. I haven't shown that in a while, so I wanted to see if I still remember it. So 0 is in the graph, that's fine. And then if you got like a C1 in the graph, then you know that C1 must be able to be written down as let's say V and TV for some V and V, and that's just the definition of it. And then let's say you got some constant F. This feels rather weird because F should usually be a function, or should have used lambda for this. I think. So because this map is linear, you can push this f inside. I think that's what matters in this case, is exactly what you want to do. And then, of course, this is also in the graph of v. Oh, sorry, in the graph of f, I guess. Sorry, in the graph of t. What am I doing? These are all t's. All right. So that's quite clear. And the reason is because f times v is definitely still in the vector space v, because vector spaces are closed by scalar multiplication. The stupid way to think about it in this textbook is that subspaces are closed by scalar multiplication, and a vector space is technically a subspace of itself, so it's also closed by scalar multiplication. That's like a really weird way to think about that. But I think maybe they avoided using that definition in the beginning because they thought it was not a really important definition, and they left it for subspaces. But I don't know why they did that. Perhaps they even wrote that it's closed under scalar multiplication, but I just don't remember it. But I do remember that that's the case for subspaces. So you have something like this, and there's only one thing left to show, that C1 plus C2 is still in the graph of t. This should be a t. Let's say C1 can be written as V1 and TV1, and C2 can be written as V2 and TV2. Then it becomes clear that C1 plus C2 is equal to V1 plus V2 and TV1 plus TV2. And here you just have to use the property of linear maps, the addition property C. And then you know that this is going to be as well as this, and these two are equal. So this is definitely in the graph of t. So yeah, this is just pretty much very straightforward proof going this way. Going backwards, I suspect that there will be much more, you'll encounter much more difficulties perhaps. So let's go the other way. So if the graph of t is a subspace of v and w, so then what's going to happen? Well, that's kind of difficult to know, but alright, give me a second to think about this. Okay, actually, you know what? I think I will think about this for a while and upload another video for this, because look, I thought I was on a streak tonight where I could solve more than 4 bloody linear algebra questions, but I guess not. Look, this has been painful. Let's see, my professor already up to chapter 5. I think he's done with chapter 5. He's shown us mercy, so he's slowed down, and he's only finished chapter 5. He was supposed to be finishing chapter 6 by now, so I'm grateful for that. But I'm still not up to date because of my stubbornness, and trying to do every single question in the book has probably not been a good idea. Even though I have been reading ahead, I've read all of chapter 4, and I've read portions of chapter 5 where I feel like the concepts feel like they're not challenging enough for me to be panicking, but I should certainly get started on this for the homework if I want to get anywhere. Honestly, just reading the textbook and doing the homework is not going to be enough anyways, because like you don't get an understanding like that. You just barely scrape by in the class and you forget everything afterwards, and then what's the point? You don't drill it down. There's no point to this. Okay, actually I think I'll cut that ramble out.